So yesterday we started talking about the two different phases of the quantumizing model that on any lattice, actually any graph, it has this form. And we have seen that there are two phases. So the paramagnetic phase in which, so this is G large, in which the ground state is unique, and in the limit G going to infinity, the ground state is just the tensor product in the x direction. Also, let's remember that there is a gap, delta E, above the ground state. And we have seen that the magnetization M that is defined as 1 over n, the expectation value of all the sigma z is exponentially decaying and 0 for G infinity. And perturbation theory and the exact solution will show that psi scales like delta E to the minus 1. Sorry. So this is a different form. I wanted. So this one is 0. Whereas the connected correlation function have this form. And actually, we commented that it doesn't make a difference in this phase, the connected and disconnected correlation functions. All right. Whereas the other phase that we call ferromagnetic for G small as a degenerate ground state, which for G equals 0 is the span of these two states. Namely, all spins up and all spins down. There is also here, there is a gap above the ground state manifold. And now the magnetization, defined in the very same way, is some number n0 of G that does not depend, that only depends on G, and which is equal 1 for G equals 0. If you compute it in perturbation theory, you would see something like this. Okay? Up to a certain point where you will see that perturbation theory fails, and it is the critical point that distinguishes the ferromagnetic phase. It's called ferromagnetic because there is a spontaneous magnetization in the z direction, and the paramagnetic phase. And then we looked at the correlation functions again. And now these one are the not connected ones. And we saw that they are different from 0. And this, in fact, it is this number that depends on G. So you see that there is no way of continuing this function analytically to this function. So in between, there must be some critical point. Okay? Means that the ground state, because these are expectation values, right? So the ground state must be non-analytic in order to have an expectation value that is not analytic. Okay, so this is what we saw. And we started to talk about spontaneous symmetry breaking. So the main topic of this lecture is spontaneous symmetry breaking, which is a very important, very, very important topic. That goes beyond just condensed matter theory. And it has implications in foundations of quantum mechanics, high energy theory, everything, okay? So first of all, we noticed that whereas this Hamiltonian has a Z2 symmetry that we called T, namely all the spin can be flipped. And this ground state has Z2 symmetry. Whereas here, in the ferromagnetic phase, it depends. Okay? So how do we see that? So we take psi 0 in the ground state manifold in the ferromagnetic phase. So this is the density matrix. And we check whether this state commutes with our symmetry. And also we want to be quantitative about it. So we want to know how much it commutes. So let me take this occasion to introduce. So yesterday I introduced the operator norm, but we, so a little mathematical detour, norms for operators. So we will use this family of norms called Schatten P norms, are defined in this way. So the P norm of an operator A is the P root of the trace of A dagger A P over 2. These norms have two important properties. The first one is the following, is that if P is larger than Q, then AP is smaller or equal of AQ, so they are non-increasing. And the second one is that they are unitarily invariant, meaning that the P norm of A is equal to the P norm of U A V dagger P, where U, V are unitary, any unitary operators. Some remarks for P equal infinity. this is equal to the operator norm. One can prove that. And we will also be interested often in the one norm, which is just the trace of a dagger A, or square root of a dagger A. The one for P equal to is called Frobenius norm, in case you encounter it. And it is what you would have if you treat A as a vector.
Excuse me, I have a question. What happens when P is equal to infinity then?
Well, if you take this limit, you can prove that this object becomes just, you see, because you see this guy, this is the A dagger A, you can think it's like the singular values of the matrix. So when you take the powers, for a large power, only the largest eigenvalues count.
Yeah.
Okay, so when P is very, very, very large, only the highest eigenvalue count. And you know that the highest eigenvalue of an operator, it's the operator norm. So for P infinity, this becomes, maybe I didn't write well, this is the operator norm that was defined, like yesterday I said that the soup of these guys. Okay? So in whatever norm you use, in this case, this is max for these states. So these states are maximally symmetry breaking. And it is 0 only for these two states that we call psi plus, psi minus, that are the symmetric and antisymmetric combination of the two maximally breaking ones. So an important remark that we will try to understand is that if we look at the connected correlation functions in this phase, they are also 0 unless we are in these states. So Cij different from 0 connected for these states, those that do not break the symmetry. Then we will understand why this is an important remark. By the way, the fact that, so in the literature there is a bit of ambiguity to this. So the fact that correlation functions are different from 0 regardless of the distance, you see this number does not depend on the distance between I and j. I remind you that Cij is defined like sigma zi, sigma zj, minus sigma zi, sigma zj. Okay? So the I minus j is the distance between the spin at I, the spin at j. So here we have correlations at every distance that do not depend on the distance. This is called a long-range order. So depending on the texts, sometimes you find this statement for non-connected correlation functions. Sometimes you find it for connected correlation functions. So the way we prefer to talk about this is that the fact that we have a phase with a degenerate ground state is shown in the fact that there is a combination of these degenerate ground states such that you have long-range order in the connected correlation functions. Okay? So we will usually use the concept of long-range order for connected correlation functions. And the fact that there are some states in which you have this is a sign of the fact that, that you have degeneracy due to symmetry. So that you are in a different type of phase. Whereas here, there is no degeneracy because the symmetry is preserved in the ground state. Is this clear? Why this is a sign of the degeneracy, I will explain in a little bit. So what we are trying to say is the following thing, is that if we have a gap above the ground state, and the ground state is unique, it seems that there is no long-range order. It has connected correlation functions decay exponentially. Whereas it seems that even if there is a gap and there is a degeneracy, at least in this case, so that's why these are not strict implications, it's just some hint, there is a long-range order in the sense that we just defined, that there are some combinations in which also the connected correlation functions do not depend on the distance. So we would like to understand how, so these are things that you can, this behavior of the correlation functions, today in the afternoon you will see it in perturbation theory, and then later we will see it by showing the exact solution of this model. But we would like to understand whether this is just a property of the quantumizing model or it's the property of symmetry breaking. And in fact, this is the case. So we will see, in particular, we will see this very important theorem, one of the most important facts in quantum many-body physics, that in general, if your ground state is unique and you have a gap, then associated to this gap, there is a correlation length, and correlation functions decay exponentially. You use this thing all the time. Also in a high energy theory, you see that propagators decay exponentially if you have a mass, right? That you usually say that the mass, so the mass plays the role of energy, and that there is a correlation length that is the inverse of it, right? So this thing is usually assumed or shown in some specific calculation for some quantum field theory, but we will prove it in general. By in general, I mean for every lattice model. And actually, this is a very complicated proof, but it is so instructive, and the tools that you use are so important that then you can do a lot of research with it. And it's also a very recent proof, because it has been proved in general by Matthew Hastings in a very remarkable paper from, I think, 2004 or 2005. Yeah?
Do you think of the second case as just the first case where delta E is going to 0? Because if there's degeneracy, it's like there's no...
Yeah, so you can see it in that way. You can see it like, regardless whether there is a gap above the ground state manifold, you could interpret degeneracy as the fact that there is no gap between those two states.
So it's like chi going to infinity?
What?
Or sorry, chi going to infinity, right? It's like the inverse of the energy?
Yeah.
Okay.
So,
that's why
so there is no correlation length, right?
Yeah.
So so you would like to understand whether this is really true. So in this case, it's true. So we will prove this, and we would like to understand if this is also a necessary condition. So in this case, we see that if we have a degeneracy, then we can use this degeneracy to make a symmetric or antisymmetric superposition, and such that the correlation functions are non-vanishing at a long distance. But is this always the case? So is it possible to have a degenerate ground state and correlation functions that decay exponentially? So if there is spontaneous symmetry breaking, the answer is not. So if the degeneracy is due to the fact that there is a symmetry that is broken, the answer is no. What we show here is typical. Every time you do a superposition of two maximally breaking states, you always have non-vanishing correlation functions. And the reason is that, you see, the correlation functions are defined in terms of sigma z here. And what is sigma z? Sigma z is the operator that spontaneously takes a non-vanishing value. And as you can see, it's a local operator. Okay, so this is very important. We will see it in a second. So the very fact that there is a local operator that takes a 0 value in one phase and a value different from 0 in the other phase, so this is called local order parameter. It's a consequence of spontaneous symmetry breaking. It is also responsible for the fact that correlation functions behave in this way. So if you accept this, that we will show in more detail later, then the standing question is, do we have ways of having a degeneracy without symmetry breaking? So for a very long time, it has been thought that no, that the only way of having phase transitions was between breaking or not breaking some symmetry or breaking it in different ways. So that the patterns of symmetry breaking would label all the phases of a quantum many-body system. But recently, in the past 10 years, it has been discovered with the work of many people, but mainly because of the work of Xiaogang Wen, that there are other forms of order that do not rely on symmetry, and that are called topological orders. So what we will do next week is to see this type of orders that go beyond symmetry breaking. So there are new phases of the matter that are only possible in quantum mechanics, whereas symmetry breaking, there is also classical symmetry breaking. So if you write the Ising model for the classical system, you have the same type of symmetry breaking. Okay. So which takes me to the next topic that has to do with the spontaneous symmetry breaking. Why spontaneous symmetry breaking in quantum mechanics is more complicated to understand. So let me show you the difference between the classical SSB and the quantum.
So, what is the main conclusion of the paper by Hastings?
This one.
This one.
This one. If you have a unique ground state and a gap above it, correlation functions must decay exponentially. This is a fact that everyone who has studied quantum math or quantum field theory has used all the time, but it has only been shown in some calculations. But this is a general proof that is valid in every dimension, not just in 1D. I think the first ones to prove it in 1D were Lieb, Mattis, and Schutz. But this is a much more elegant proof. And by this I mean that the tools that you need to learn, and we will learn all of them, are, they are a very beautiful toolbox that can be used for future research. They almost suggest to you what to do next. Okay, so in classical spontaneous symmetry breaking, you have these two states that are the degenerate ground states of your rising Hamiltonian. So we are in the limit of G going to 0. So in this case, the Hamiltonian is some energy. Let me just call it again S. That is something like this. And these numbers can be +1 or -1. And so they are not cats, but SI equal +1 is the first configuration that minimizes the energy, and SI equal -1 is the second configuration that minimizes the energy, okay? And why we say that there is a spontaneous symmetry breaking is because you can show that. So there are two ways of showing that. One, that is what you usually find in the textbooks, it's called the method of external fields. So what you do is that you add to your energy as epsilon small external field, say in the plus direction. Then you compute your average of magnetization. You take the thermodynamic limit. Then you send this external field to 0. And you see that your system is stuck at 0 temperature in this state. That instead of averaging over all the possible configurations, you can only average on those where there are many plus. What this means physically, it's not super clear. Usually in books you find something like, oh, this shows the importance of the initial conditions because this field that you add is like an initial condition. But it is like, So there is a more convincing dynamical argument that has to do with ergodicity breaking that I will show you later, because it's the same for classical and quantum. But other than that, there is no other question that we should ask, because this is a classical model. We cannot make superpositions of these things. Okay? So there are only two states. But now your minimum energy is in a subspace. It's the span of these two states. And here, spontaneous symmetry breaking means that the system will not be found in any possible superposition of this, but either in this or in this. So you see that SSB means that a basis is chosen. So this basis is favorite. I could use this basis, right? Where are they? Those two states also are orthogonal. But the system doesn't choose between this and this. or any other superposition, it chooses between the maximally symmetry breaking ones. That's why the symmetry breaking is spontaneous. So a basis, this one, not this one, is chosen. And now this is weird, right? Because in physics, we are so used to the fact that all our physical statements must be basis independent. But now we see something that is basis dependent. So there is some mechanism in nature that chooses a basis. As you can see, the difference between these states and these states, so you see the n is large, so these are macroscopic states. It's the same difference that we have in the so-called paradox of the Schrödinger cat. This is cat alive, this is cat dead, and these are the coherent superpositions of the two symmetric and asymmetric of the two states. So a basis is chosen means that the system spontaneously chooses whether the cat is alive or dead, and that's why we don't see it. But so far, I'm just saying this, right? I'm not giving any explanation. I'm just saying a basis is chosen. So we want to understand this. So why? And so this argument can be made in many ways. And the most famous way is the coherence. So no, let me use this part. But here I will show a slightly different, it's still in some sense the coherence, but it's more apt to our quantum many-body way of thinking, and also raises some possible questions for the future. Okay, so let me see what I want to say. All right. So first of all, one remark. As we said, 0 and 1, so in this limit, so the limit of G infinity, we said these are classical states. Why do we say that these are classical states? Because there are no fluctuations in these states. In this basis, there are no fluctuations. It's not the coherent superposition of something else. However, this statement that it's very easy to understand, it is a bit ambiguous, right? Because it seems a bit circular, because of course I can write this as a coherent superposition of these two. So in what sense there are no quantum fluctuations? It depends what observables you are looking at. So this has no quantum fluctuations in those observables that are also a tensor product in the same basis. So it's a bit circular, this thing. So we will try to say that these are classical states by looking at another property of quantum mechanics that is the most important property of quantum mechanics, that is entanglement. Okay? So who of you knows anything about entanglement? Do you know what it is? So you know that every time I write a state like a cat, this means that this is a pure state. Okay, so we saw this yesterday, means that the density matrix of this state, or of this state of any pure state, can be written like 1, 0, 0, 0. Okay, there is a basis in which this is true. Now you see, this is a probability distribution. This only means that we have probability 1 of being in this state, and then probability 0 of being in other states. So all the possible fluctuations come solely from the fact that inside one state there are quantum fluctuations. But there are no additional fluctuations due to the fact that you don't know in what state you are. But in general, you could write a state like a probability distribution over states like this. So if you do this, this would look like, because this becomes a basis, becomes something like this. So this means I have probability P1 of being in the state psi1, probability P2 in being in the state psi2, and so on and so forth. So this is a classical probability distribution. I just have some uncertainty in how my system is prepared. This is or if you wish, this is an ensemble of states. Plus, each of these states has its own fluctuations because it's quantum. So you see, classical and quantum fluctuations mix. Now, so both are probability distributions, so they both sum to 1, which is, that's why the trace of psi is 1. However, you see that these two probability distributions have a different disorder, if you wish. This is very ordered, right? There is no uncertainty. Imagine that I'm sending a message, and the message, so it's written in the Latin alphabet, so it's a certain number of A's, a certain number of B's, a certain number of C, and I want to know how much I can compress it. Imagine my message is only A. So the probability of finding A is 1. Then it's very easy to compress. I don't need to send the whole string of characters. I just send 1. So you see that this probability distribution means that there is little disorder, so high compressibility in terms of information theory. And if they were all the same, 1 over n, 1 over n, 1 over n, I would have maximum disorder or maximum entropy. So what is a quantity that captures this? That is maximum, it's minimum when I have this probability distribution, and maximum when I have 1 over n, 1 over n, 1 over n. Instead of the trace of psi, it's the trace of psi square. Right? Because this can go from 1, in this case, to 1 over n. Because this is equal to 1 over n squared many times. How many times? N, because I have n eigenvalues. That is 1 over n. So this quantity is called purity. Tells me how pure is my state. And because n is an exponential number, so when you have exponentials, then it's better to use logs. And now we want to write it as an entropy. So because this is 1 over n squared, but so we want this number to be positive when I have a lot of impurity. So I will say the entropy is minus log of the trace of my psi square. And let me put a 2 here that I'll explain. Okay, so this is a way to measure how mixed is my state. Why I put a 2? because I can actually build a family of entropies that all have this property, that are monotones as I mix more and more the state, and are called Rényi entropy. And so they have one parameter alpha, and they're defined in this way. So that's why I call that S2, because if for alpha equal 2, you get that. Exercise, I believe, is part of the homeworks. Show that in the limit alpha going to 1, S1 is minus, let me see how I want to write it. Let me write it this way, where these are the probability distributions of my density matrix. If you remember thermodynamics, this is the thermodynamic entropy. In information theory, it's called the Shannon entropy because it's the precise quantity that you need to compute in order to know exactly how compressible is a message. Okay, so in the quantum case, this is called von Neumann entropy. So the von Neumann entropy is 0 for a pure state. Okay. Now, why I say that these states are classical? Because now imagine that my state, that is this tensor product, I imagine it, I can write it in this way. I have some 0. So these are all my spins. And now I split I take one set of spins that I call A, and the rest is B. So I can write this state, all spins up. It's tantamount to say all spins up on A and all spins up on B, right? It's a triviality. And now imagine that I can look. I do not have access to B. In fact, this is not just some mathematical hypothesis. If you remember our first lecture, we know that we can only use quasi-local observables, that they're the only physical observables. Otherwise, the thermodynamic limit will not be possible. So imagine that the only observables we have access to are in A. So this means that every time, when I compute an expectation value, so my observable O, in fact, has a support in A, right? This is what it means. So it can be written in this way. And every time I compute an expectation value of this observable in this state, I don't know if you ever did it, but if you didn't do it as an exercise. It's a very simple exercise. This is the same than taking the trace of just OA in the state psi A. So you see, this is an observable on the full Hilbert space. It's an observable on the Hilbert space of A, where psi A is defined like the trace over B of psi. And we call it reduced density matrix, or marginal state. Okay. So from now on, every time I'm taking the expectation value of some local observable, is the same thing than taking the expectation value of that observable on the reduced state. So now let's look. So what is psi A in this case? Well, you just need to trace out this, right, by definition. So this means that, so this is my full state. And I trace out B. And what I get is not surprisingly 0 on A, 0 on A. Which is again on a smaller Hilbert space, but it's still. So now, how many eigenvalues I have is the dimension of the Hilbert space associated to A, but still 1, 0, 0, 0, 0. It's still a pure state. In other words, if I ignore what happens in B, I don't change my state in A. This is what happens in classical physics. For instance, if I make measurements on B such that then B is not part of my description anymore, and then I am only left with A, the fact that I've measured B does not change what I have in A. So this is classical state. That's why we say it's a classical state. So in other words, classical states are such that locally they're still pure. So their entropy is always 0, globally and locally. But now let's look at our state psi plus. That, as we say, is 1 over square root of 2 of 0 tensor n plus 1 tensor n. And let's do the same thing, right? Let's take psi plus A, which is the trace over B of the full density matrix of psi plus. So it's very immediate to see that this would be equal to 0A, 0A, 1/2, plus 1/2, 1A, 1A. So while before I have probability 1 in being in the state all spins up on A, now the marginal state 2 of A is the mixed state with 1/2 probability of being all spins up and 1/2 probability of being all spins down. So the entropy of psi A, if you compute it in this way, will be equal minus 1/2 log 1/2. The logs are in base 2, minus 1/2 log 1/2, 1. We have entropy 1. Notice also that on this Hilbert space, no, forget about it. We have entropy 1. Okay, so that's why we say this is a quantum state. So one thing that we would like to say is that our claim that spontaneous symmetry breaking means that those states are chosen, we could try to rephrase it in this way, that the states that are chosen are the classical ones, the ones that are not entangled. Because I used this word entanglement. This is what entanglement is. A state is entangled if its reduced state has an entropy, a pure state. A pure state is entangled. There is a generalization to mixed states, but we will not go there now. So pure states have entropy 0 And we say that a pure state is entangled if its marginal state has a non-vanishing entropy. So the point of view that we will take here is that entanglement is the fact that you have local entropy, but not global entropy, which is pretty amazing. In fact, it's only true in quantum mechanics, and only quantum mechanics has this property. There is another way of reading this property, is that given a state that is mixed, is it always true that it's mixed because it's the marginal state of a pure state? So is there a bigger Hilbert space in which there is a pure state such that its marginal state is this one? The answer is yes. So every quantum state can be purified. And this is, together with other very reasonable hypotheses, if you don't know anything about Hilbert spaces and quantum mechanics, and you start with this as a postulate, you can recover quantum mechanics. So purification is the defining property of quantum mechanics, and which means entanglement. So this intuition of Schrödinger that entanglement is the defining characteristic of quantum mechanics, it has been proven true. So for us, so this detour about entanglement seems that we can say that the classical states are those that are chosen by spontaneous symmetry breaking. Okay, see, you know, am I sweeping something under the rug, or it's all good? No, I'm sweeping something important under the rug. Because, you see, spontaneous symmetry breaking happens in the whole phase. So up to GC, you have two states that are maximally breaking the symmetry, and not just when G is equal 0, G is equal infinity. Okay? So so this statement is very easy to show that the chosen states are the classical ones. When what is G? When G is equal 0. Okay, but what happens for small g? So now the two states that break the symmetry that are called psi1 and psi2. So these are, by definition, I call these ones the maximally symmetry breaking ones. And then I can still define psi plus and psi minus as psi1 plus minus psi2. Okay? So is it still true that these are the most classical ones? Well, now it's complicated. Because now psi1 does not have the form all spins up or any other product state form. It's not like this. So already this state is entangled. And in fact, could be more entangled than these states as a function of G. What I mean is that, so this is a function of G, right, for small g. That there are, it could be the entropy of psi1 for some G is greater than the entropy of psi plus for some other G, but with the G in the same phase. So we cannot simply say, oh, these states are the most classical ones. It's a pity because we really like this statement that I make here. Because we really want to, when we understand the coherence, we really want to say, oh, you know, this has to do with the fact that we do not see Schrödinger cats. So, but the argument, the way I did it doesn't work. Okay? So we need to do something a little bit more sophisticated than that. Yeah. in 3 minutes. So what we can do is the following. So these are my spins. And now, instead of dividing it in A and B, I have A, another block B, and the rest is called the C. So again, for G equals 0, we know that our states are all spins up and all spins down. So I can write psi plus in this way, because nothing really changed. But now I can write 0 on A times 0 on B times 0 on C plus 1 on A, 1 on B, and 1 of C. And by the same token as before, every time I take the reduced density matrix, so I trace out B and C, then I have 1/2 0A, 0A, plus 1/2 1A, 1A. Or I trace out A and C, and have the same thing on B. Or I trace out just C, and then I have the same thing on AB. So in general, I can write this in this way: whatever value X takes, whatever subset I see. Okay? Whereas, no matter in this state, all spins up, no matter what I look at, I always get a pure state. So now look at this quantity. It's called mutual information. This is the notation. And it's defined as the entropy of the reduced state to A plus the one of the reduced state to B minus the one of the reduced state to A and B together. So when I only trace out C. So you see that for the psi plus state and for the psi1 state, so the psi1 state is always pure no matter what I do. So I get 0 plus 0 minus 0, and there is no mutual information between the part A and the part B. But here, no matter what I do, I get this type of state. So I get the probability distribution 1/2 and 1/2 that, as we saw before, gives me entropy 1. So this is 1 plus 1 minus 1 equal 1. Okay? So far, I've not done anything more than before. I mean, it's more complicated, but I get the same result. Also before, I would get 1 and 0. However, now I get a handle on the problem in this way. Because when G is not 0, so my states are not like this anymore. As we said, our psi1s are entangled. So these guys will not be 0, 0, and 0. I will have, for psi1 in general, for small g, I will have the entropy of psi1 plus the entropy on the reduced state. So I can do like this, psi1a, psi1b, okay. So now we is it really true that Schrödinger cats do not exist? After all, we do quantum mechanics, right? So we have experiments in which we know that there was a coherent superposition. The fact is that those are microscopic. No, they are not superpositions of this type. They are superpositions on a few degrees of freedom. So if now I consider, so you see, when I have a macroscopic superposition, this quantity, so like here, is different from 0 no matter how big is A, no matter how big is B, and no matter how distant they are. So it means that there is a coherence between the state of the cat at its nose and its tail, which is the weird thing. It's not weird that some protein or of the cat in some cell is in a coherent superposition. It's weird that the nose and the tail are in a coherent superposition. So our requirement is that this can be different from 0, but goes to 0 for DAB large and A and B themselves large. So this would not rule out every superposition, but just the macroscopic ones. So if we want to show that spontaneous symmetry breaking chooses the states psi1 and psi2, the maximally symmetry breaking ones, we have to show this. And we will do that. But we will need to learn some technical tools. And very interestingly, they are part of the same toolbox that we need to prove Hastings theorem. Okay. Why? Because all these tools are the exploitation of the fact that we want to look at the interplay between something that has some global characteristic, like being far apart, being large, and the fact that our algebra of operators is local. So we will basically learn all these tools, and we'll be able to prove a bunch of very important things in quantum many-body theory using this. So tomorrow, we will start doing that. But tomorrow we will also do, so our discussion on spontaneous symmetry breaking is not finished because yesterday I said something, so, once I've said, okay, the system spontaneously chooses the most classical ones, okay, this is a good understanding of something, but we still don't know why, okay? So we need to show two things, that they are the most classical ones in this sense, the most macroscopically classical ones, and that there is a reason why this happens, and the reason is that they are the stable ones. And we also shall see this tomorrow, okay? Thank you.